Okay, all right. It's a little early, but I just wanted to start. I just returned the homework number 2. All right. Yeah, so that's one thing. And another thing, yeah. Probably, let me lower the speaker a little bit. It's probably confusion coming from crop physiology course regarding terminology. So I use canopy to mean the plant community. And canopy sometimes means the surface of the plant community. But in my lecture, I like to stick with my definition so that it's consistent. So that the whole plant community is the canopy, not just the surface. So remember, there's a super important exercise question. What is the difference between canopy photosynthesis and single leaf photosynthesis, and why? This is very important. This is one milestone question. You are supposed to understand why and supposed to answer that question. So I saw students confused by stating canopy photosynthesis meaning that only the surface, not the entire stand. Okay? All right. Okay. Whenever I see that, I give you the feedback so that you can correct misunderstanding. Okay, good. So that's why we are doing this. All right. Any questions regarding that? All right. So the last week, Wednesday, we learned about wind effect, right? Air velocity, wind velocity affecting plants through gas exchange, and then we learned the concept of boundary layer. And wind is affecting boundary layer. So I got questions from some of you guys asking the efficacy of vertical airflow in a greenhouse relative to horizontal airflow. Yes, if you are willing to maximize the photosynthesis, vertical airflow is probably the way to go rather than horizontal airflow. But right now, the priority is temperature uniformity. And that's very important too. And today's lecture is temperature environment for the plants. Okay? So it's all connected. It's all connected. You probably already realized that. All right. Okay. But if someone can, invent a technology that can move the air through the canopy and then also, maximize the uniformity or optimize the uniformity, that would be nice. That would be nice. So engineers, you can work on that to make it happen at relatively low cost. Okay? All right. Big topic. So, temperature. So 2 readings there already uploaded. The first one is for everyone. It's Hanan's chapter, Temperature, so the general understanding of temperature influence on plants. And then the second one is, it's a conference paper. Hold on a second. I'm just turning this off. Yep. And this is a conference paper written by Romo, I think, Romo and Royal Hines. Those are floriculture plant physiologists. One is from Norway, the other one is from Michigan State University. And that is talking about one technology I'm talking about today using temperature response of the plants. So 2 papers. The second one is additional. Yes, TJ. Okay, any question? All right. Okay, so temperature is very important, right, for plant because all the function is based on enzyme activities, basically, or involved at least, some enzyme activities. Enzyme function is depending on the temperature. So that's why we pay attention to that. Plants are in the optimum range of temperature. And if you remember the greenhouse technology, it was originally developed as a season extension by controlling temperature or maintaining temperature a little bit warmer particularly during winter time. It's outside is way too harsh to grow plants, too cold. But if you have a one envelope, covering the surface, then you might be able to grow a little bit longer, than nature or the natural temperature environment. So that's how greenhouse technology developed. So the temperature is very important, therefore the main controlling variable in a greenhouse, and then also growth chamber, right? Okay, so how does it respond? So this is a simplified or generalized version of the response of photosynthesis and respiration to the temperature. Okay, photosynthesis and respiration to the temperature. So the respiration and photosynthesis are two different ways to respond. Respiration within this temperature range, it's almost exponentially increasing with increasing temperature. And beyond that, it eventually, drop down because of enzyme, breaking down or losing the function. Photosynthesis, if you remember, the real photosynthesis is gross photosynthesis, and then gross photosynthesis minus respiration is the net photosynthesis. Okay, so if you look at the gross photosynthesis, it's increasing with increasing temperature and then level off. That's a kind of general understanding of gross photosynthesis responding. So this particular bending point is depending on the species. So this is just one example, but the shape is probably similar to similar, plant species. And so gross photosynthesis minus this exponentially increasing respiration. Therefore, if you look at the net photosynthesis, its response to the temperature, then you see clear peak temperature somewhere. All right, in this case, like 15 degrees, which seems like a little bit low for most of the greenhouse crop. But so it's generally, the generalized understanding is some peak in there. Okay? All right. So the temperature is increasing and then response is increasing, but if it is net photosynthesis, sort of level off or just peak at certain temperature. And respiration is exponentially increasing, right? So two different response. Okay, so this one is my sort of old and not really well, high quality scan, but this is my favorite chart to make the point of temperature in the air is very different from plant temperature. So this is outside in the field. Sensor was in an apple leaf, so it's not even a greenhouse crop. But you can see that this is within the 18 minutes, relatively short period of time. Okay, and then probably Washington State or somewhere, the weather is fluctuating, sunny and cloudy and hazy within that short period of time. And then the black line is the air temperature. It's not large, up and down, relatively consistent. It's outside, okay, 18 minutes. Leaf temperature, on the other hand, fluctuates really largely compared to air temperature. Okay, so the air temperature under the sunny, the sky condition, air temperature was about 21 degrees C, but look at the leaf temperature, which is reaching 25 or exceeding 25 degrees C, 4 degrees greater than air temperature. Okay, and then as soon as weather changes, maybe wind blowing and the reducing boundary layer, leaf temperature start dropping, even though it is still sunny, and then it enters the condition of cloudy, cloudy weather, and now air temperature is higher than leaf temperature. Leaf temperature is lower than air temperature, about 1 degree C in this case. And then changing again depending on the conditions. So it is, very different, air temperature and leaf temperature. And then there are multiple factors affecting, leaf temperature. And the air temperature is actually one of the factors affecting leaf temperature. Okay, so my question, do you understand that leaf temperature is more important than air temperature? Why? Why leaf temperature is more important than leaf temperature is more important than air temperature? Caitlin?
Because the leaf temperature is also the effect of the radiation energy, and so it's going to heat up if there's sun, so it's more easily affected.
Leaf is, I don't really quite understanding. Leaf is getting radiation, so it heats up, yes?
Yeah, and that might not be the effect of that might not be seen from the air temperature.
Yeah, so air temperature may not be increasing that much. Yeah, that's true. But my question is why you want to pay attention to leaf temperature? Yeah, Ken, you are the...
It means it's respirating. If you touch a leaf and it's cold, it's actually alive.
Yeah. So you saw this this function, right? Function response to the leaf. Okay, so when temperature of the leaf is 15 degrees C, and then when temperature of the leaf is, say, 30 degrees C, you see that net photosynthetic rate is very different, right? And then that could happen even air temperature is the same, right? That's what.
Oh, he was just pointing out that something that I had missed, crucially in the question.
Okay, all right. So the leaf is driving photosynthesis based on its temperature, right? Leaf is driving photosynthesis in all the biochemical reactions based on its temperature, not based on air temperature. So that's why understanding leaf temperature is very important. Leaf temperature for photosynthesis, and maybe fruit temperature for fruit ripening, and maybe flower temperature for pollination, and maybe meristem temperature for thinking flower development or leaf development. Okay, because that particular site is the driving site of that particular process. Okay, so why we always talk about air temperature and not, like you guys, greenhouse workers or greenhouse scientists, assistants, working in greenhouse, and you pay attention to greenhouse air temperature. You enter the greenhouse, and when it is warm, you get alerted, right? It is cold when you do the same. So why you don't, like Ken said, when you touch the leaf and then it is cooler, it's good. Why you don't do that way, or why you don't put the sensor in that leaf? If you all agree, no question, right? Nobody insists that air temperature is more important than leaf temperature.
But is it
TJ.
possible to control the temperature of all the individual leaves?
Not necessarily. If you are getting so the TJ said that it's not possible to control temperature of, individual leaves. That's a really good point. So the leaf temperature, it's important, but which leaf to measure, right, to represent the entire greenhouse is always the question and always the challenge. And then when we do the greenhouse lab in April, we all go out with a bunch of sensors and then measure the temperature distribution in the greenhouse. And then hopefully you see that the large difference in temperature, top of the canopy, middle of the canopy, north side and south side. And you can actually quantify that. Okay, so in that situation, which temperature should we use? We don't have a good representative. And then also it is very challenging to accurately measure leaf temperature because temperature sensor is affected by radiation and all that. So that's why we kind of compromise by measuring air temperature because air temperature is one of the important factors. So that's what is happening most of the cases, all right? So, all right. So what's the factors? Other factors, radiation. Caitlin said that radiation is important factor. And then another factors, transpiration. Ken was talking about cooler temperature of the leaf, meaning cooling effect is going on by transpiration, evaporation from the surface, so the cooling, function. And then also conduction and convection, which is removing heat or adding heat to the leaf or from the leaf. So that's also another important factor for leaf temperature. And metabolic activities, particularly for fruit, big mass and doing a lot of respiration, generating heat, and that also needs to be accounted. And this understanding is going to be enriched, okay, in the section of energy balance, leaf energy balance. That is another milestone lecture for you guys. So I'm not going to talk about the detail of those factors today, okay? Right, but I like to talk about the general response of the plants to the temperature. This is, again, just like photosynthesis, but a simplified version of temperature response of the plant growth and development rate. Y-axis is temperature, and x-axis, not the other way. X-axis is temperature, and it has, ideally it's a leaf and plant temperature, but you often see that, using air temperature because of the difficulty to measure or difficulty to find the representative temperature. And then y-axis is development rate or growth rate. And then you see that increasing temperature, increasing the response, the rate of growth and development. And then there is, temperature range, nothing happens, okay? And then the growth starts or development starts at certain temperature. And this minimum temperature is called base temperature, okay, base temperature. And then from that, after that base temperature, it's a basically linear response, linear. And then reaching the optimum temperature, okay, optimum temperature, which is providing maximum rate of the response. And then after that, decline, like this. That's the typical. So important thing is there is a base temperature and there is a linear range, from base to the optimum temperature, okay? This is the base of understanding effect of average temperature and then also growth and development rate. Okay, here, so this is a chart from Grower's guidebook. So that's why unit is Fahrenheit. So it's a, I forgot the crop name actually, but it's a floriculture crop. So that's why they're looking at days to flower after the initiation of the flower buds. So how many days to get anthesis, opening the flowers. So that's what they looked at. So the shape of the curve is like opposite, right? But the meaning of this curve is the same as the previous one. Previous one is that, showing the temperature that allows the fastest development. Okay? So that's the optimum temperature. And then up to that point, it's almost linear, showing linear response. If you decline or reduce the temperature, then growth rate or development rate of the flower reduce, therefore taking more time to get to the flower. All right? So you see this kind of data, but meaning the same as the generalized version of the temperature response. Okay, so so if you look at the various literatures, you can find recommended temperature range during the day, during the night, and maybe different stages. And then I just put up the tomato recommendation. For example, day temperature 21, 26, night temperature 14, 17. Could be slightly different for different literatures. And germination is much warmer temperature usually. Okay, and those are all based on the experience, based on the tests. But you can certainly think that day temperature is affecting photosynthesis, transpiration, and flower development, and night temperature is respiration. Because the processes happening during that phase is very different. So this is another selection of information. I copied from my other presentation, so the tomato recommendation is slightly different, but basically the same. Germination, warmer temperature, day temperature 24, 26, night temperature 15, 18. That's recommended. And lettuce is much cooler temperature. And some of the lettuce case, if you have a higher temperature and longer day, then you might have bolting. Bolting is the flower development and then the stem extension with the terminal flower bud, which is not acceptable for lettuce production, which is super acceptable when you're a breeder of lettuce. You want to seize. But anyway, so the different response triggered by different temperature range at different stages. Tomato average temperature is very important, and reducing temperature does enhance flowering at young seedling stage. And when mature stage, you need to lower the temperature less than 30 to make sure the pollination is not affected. Warmer temperature pollination is affected. So that's typical heat stress. So it's all, involving some temperature effects. Other crops in here. So that's available in different literatures. So optimum temperatures, you see different optimum temperatures at different growth stages or development stages. And regarding optimum growth temperature or optimum photosynthetic temperature, that temperature is depending on different light intensity. If the light intensity is low, cloudy day, optimum temperature should be lower because respiration is concerned, and then respiration is not affected by light, right? Dark respiration is not affected by light, but still exponentially increasing, so that when gross photosynthesis, which is pretty much affected by light intensity, is reduced under cloudy day, you probably want to lower the temperature so that net photosynthetic rate is still high. Okay? You can think about that. So that's one way to exercise your understanding of temperature response, regarding different pathways of the plant physiology. And I'll explain this in a second. And then also, if you're looking at flowering or if you're looking at the ripeness of the fruit, optimum temperature gain are different. So it's not simple. It's not simple. So you need to pay attention to all sections of plants, different stages of plants to be able to optimize your production, basically. So this one, are you warm or are you okay, temperature-wise? Are you okay? All right. All right. So this chart, 3 charts together, is just showing the light response curve, net photosynthetic curve. So this is showing plant capacity of photosynthesis. This is rows, so woody plants. And then showing the decline of maximum photosynthetic rate by aging. So the more days after emergence, leaf emergence, the leaf reduced the photosynthetic rate. So this is one example of the temperature response is affected by leaf age. And then also the temperature, the same age, 20 days after emergence of the leaf, 10 degrees C, 30 degrees C, it looks like 30 is close to the optimum temperature. So just showing the example how you can see the difference. CO2 concentration affects the temperature, optimum temperature. When you have a higher CO2 concentration, plants seem to increase the optimum temperature little bit. And the reason is that it's related to Rubisco enzyme, which is basically capturing CO2. Okay, so that's the enzyme involved in the first step of Calvin cycle. And because of the affinity of enzyme with CO2 molecule is temperature driven, and at higher temperature, the affinity get lost or reduced, and therefore the impact of higher CO2 is much bigger at higher temperature range. So that's why, as a result, you start seeing this sort of peak shifting. So under the ambient, or used to be ambient, concentration of 350 micromole per mole in this particular graph, showing the peak temperature around 30 of the photosynthesis, net photosynthetic rate. But under 1,000, it seems to be 35, and then so this is typical response under high CO2. And then if you look up literatures of high CO2 influence, you should be able to find a lot more information about this. The shifting peak under high CO2. Yes.
How do you measure the net photosynthetic rate? Like, I understand it's like the gross photosynthetic rate, like at the different temperatures. Like, how do you actually measure that?
You want to know net or gross? Both. Gross. Okay, so the gross photosynthetic rate is very challenging to measure. You have to use carbon, isotope? Yeah.
I guess then technically net, because if you're varying it this much, like how do you actually measure the rate at the different? Is there like a sensor that does it?
Yeah. So the CO2 measurement or the net photosynthetic rate is very easy to measure, because you can capture the leaf or plant in a sort of chamber, maybe small chamber for small leaf or large chamber for whole plant, and then create airstream, and then using a mass balance, incoming air, how much CO2 is contained, outgoing air, how much CO2 is contained, and by knowing the flow rate of that system, then you can compute how much CO2 is consumed by the plants. So that is the typical way of measuring. And then you change the CO2 concentration of incoming air, then you can measure the high CO2 response, and then you can change the entire temperature, then you can see the temperature response. You change the illumination, and then you see the light response. So it's very simple setup you can think about for that. But gross is very challenging. All right. Okay, quite unique response. You may know by sort of observation if you grow plants in greenhouse or relatively under controlled environment. You may have seen that when temperature is lower, size of flower is bigger. Because high temperature enhance the development, so the plants tend to quickly develop flowers and many flowers, so the flower size tends to be smaller versus slow growing temperature at low temperature, flower size tends to increase. So that's a quite unique plant response. This is another example. So I have the same observation in my strawberry greenhouse. Strawberry plants tend to produce much larger flowers and therefore larger fruits during the time we have optimum temperature. But as soon as May comes in and temperature goes up in the greenhouse, and then our fruit size and the flower size are both much smaller. So it is affected by temperature. So, yes?
So you said when flowers are smaller, fruit is
Smaller flower is smaller fruit.
Okay.
Yeah,
Okay.
yeah. Okay, so let's try to understand average temperature concept. So in greenhouse plant production, and then also I think any plant production, we pay attention to average temperature to summarize what's the temperature environment they are growing. And so we often use the average temperature. But average temperature can represent the growth growth and development rate only when the temperature is in the linear temperature range of the response curve. Generally speaking, when they are in the linear range of the temperature response curve, average temperature determines the development rate of the plants, or average temperature can represent the temperature, as the temperature determining the development rate of the plants, regardless of actual changes of instantaneous fluctuation of the temperature. And particularly the case under the controlled environment, because controlled environment control temperature independent from other factors. Okay, so why is that? Before explaining why, I want to show you the evidence. So this is some other data of, this is a leaf development rate. So the number of leaves developed per day in average. So maybe they are counting number of leaves every week, and then per day rate was computed. So it was in the range of 1 to 3 leaves development per day, okay, per plant. And then they had a whole bunch of temperature. And then they had constant day and night temperature. They had higher day temperature than night temperature. They had higher night temperature than day temperature. And then if they plot the data like this, by average temperature, 24-hour average, it shows, regardless of the actual temperature combination, whether it is constant, for example, around 22 degrees, whether it was constant 22 degrees or maybe 26 degrees during the day and 18 degrees C during the night, and making the average 22, regardless of the combinations, you can explain that development rate just using the 24-hour average temperature. It's very useful. But this happens only when those temperatures are all in the linear range. Okay, if you are engineer, you probably know why, but I'm going to show you that in a minute. This is I think actually from Moore and Hines, your second reading material. Those two different species, Chrysanthemum and Campanula, showing the optimum temperature different. Campanula warmer temperature optimum 23, and Chrysanthemum a little bit lower. Again, this is time to flower, so that's why the curve is dented rather than peaked, but meaning the same, the fastest growth or development occurring at that temperature. Two species different, but also it's comparing different combinations of temperature and then showing that regardless of the temperature combinations, 24-hour average temperature explains the development rate. Right, so within the linear range, average fluctuation or less fluctuation, and then as long as average is the same, you can expect the same, rate of the development. If the average temperature is different, in this case 2 degrees C, then you have to expect that difference growth and development rate, because temperature is different, average temperature is different. But fluctuation doesn't matter as long as it is within the linear. So here is a range of fluctuation to understand that in this typical temperature response curve. So let's say this is a temperature T1, temperature T2. That's the range of temperature you had in that growing, conditions. It's fluctuating, all right? And then average temperature is right here, okay? T1 and T2. Let's say T1 and T2 divided by 2 in the middle point, that's the average, okay? And then if you look at the growth rate or development rate, the average is actually the corresponding rate at the average temperature because it's a linear response. Makes sense, right? As soon as it is off the linear, then average temperature of T1, T2, so the much larger fluctuation covering outside of the optimum or linear range. In that case, average temperature is here, and corresponding response on that curve is actually off from the average of those two rates. So that rate 1 is at T1 and rate 2 is at T2. So the average rate should be here, but if you use this response curve, the average response should be right here. So that means when temperature range exceeds the linear range, then you can't really use average temperature to represent the plant growth rate or development rate. Okay? It's not too complicated, I hope. All right. So day temperature affect photosynthesis and transpiration, and dark temperature or dark period temperature affect dark respiration rate, and then also elongation. In the lecture of week 3, I started talking about stem elongation. And one thing I didn't really clear that day was the stem elongation happens at night. The plants elongate the stem during the night. So that's why night temperature affects the stem elongation. If you keep the plants warmer, then you probably see more stretch of the plants. So those are affected by night temperature. And development rate is affected by generally the average temperature, 24-hour average temperature. And you may know by experience or by observation, in growing facilities, night temperature is usually lower than day temperature, and then that is quite natural way to do that. That way you can reduce the respiration rate during the night, so that saving the carbohydrate produced during the day, so you can maximize or you can expect the production rate. And growers sometimes try to reduce night temperature further down, particularly in northern climates. Heating is happening, and then greenhouse heating cost is too much, and then they want to reduce the cost, and then by lowering the set point. And then in that case, respiration is affected, so it may be saving also, but the 24 average temperature is also affected by lowering night temperature, right, because it's 24 hours. And then that lowered average temperature slow down the growth. So when you tweak the temperature in the greenhouse or production system, you got to pay attention what you are doing. For example, if you decide to lower the night temperature, you have to think that, so what happens, what does it mean, or what it means regarding 24-hour average temperature. Okay, so that's multidimensional thinking of temperature management. Okay, and so some growers do a more strategic control of night temperature. They want to reduce night temperature to save energy. They want to reduce the night temperature so that plants do not consume too much, energy. But they want to keep going the development rate. And in that case, they increase intentionally the day temperature whenever they can. For example, in sunny Arizona or desert Southwest, you have a lot of radiation during the day, even during winter time, so that you have opportunity to set the higher temperature in a greenhouse. So the average temperature is the same, but having lower night temperature to reduce the costs or reduce the respiration rate a little bit. So those kind of things, you can do that by understanding temperature response. And then also growers typically do quick temperature change at the beginning of the night so that the fruit sugar translocation, no, the leaf sugar translocation to the fruit is more enhanced. So that's why you might hear growers talking about that. Dave, I'm going to talk about that interesting technique in a minute. All right, so if you are field growers or doing agronomic study as research, you probably know heat unit, right? Degree days, heat unit. So that's used for expressing or, so that is used as a major factor to estimate the potential growth of the crop in a field. And heat unit or degree days is very effective because temperature and radiation in the field is pretty much correlated in the field. So they don't have to use radiation in, for example, growth modeling. So the growth and development pretty much explained by using temperature in the field. But in the greenhouse, this may not be true because your temperature is completely separated from usually the radiation level. But anyway, so I just wanted to show because some of you are familiar with this. So because of the temperature influence, you can use the average temperature and minus base temperature as the minimum unit to accumulate. And then you think that the proportional amount of growth is going to be accumulated, okay, by day. So by knowing temperature, over time, and then also typical temperature of the season, you can predict, for example, flowering timing or fruit production, harvestable timing by knowing the temperature. And this is a typical tool for open field growers to do that. Greenhouse growers use sort of as one tool, but not the major. But the open field, they do that. So cumulative heat units, so this is a one daily heat unit. So the 1 day maximum temperature, minimum temperature divided by 2, that's the average daily temperature, minus base temperature. The base temperature is the minimum temperature starting the positive growth rate. So the beginning of the linear range. And then you get daily heat unit, and then cumulative, so the sigma of that daily heat unit for the entire production period or whatever the specific production period is the heat unit. Okay. Yeah, and then this works really well for the mild climate. However, in Arizona, because we have way too high temperature in outside field, right? So not just considering low end, we want to consider high end too, because often temperature exceeds the optimum temperature, so no longer linear range. In greenhouse, you probably don't need to think about upper limitation because most of the case you try to maintain temperature within the linear range anyway. So what we do in the open field, as an example, in Arizona, set the upper limit and lower limit and compute the cumulative temperature of that day. And that way, this is the way more accurate than just using base temperature. And this is the way you can find the value, or this is the way the values are computed in the website of ASME, Arizona Meteorological Network. So if you go that link, you can find more information if you're interested. Any questions regarding? Yes, TJ.
Are there resources to find like maximum temperatures for certain crops?
Mm.
Then if not, if we're in the greenhouse and we're growing like the tomatoes or the cucumbers, and say we're like 35 degrees Celsius for a couple hours in the peak of the summer, but then we're able to drop it so that average is really what we're going for. It doesn't matter if you get a little hot, the plants can take it. But if we can keep our average, then at least we're in that efficiency range.
Yeah, so you have many questions. Okay, so maximum temperature information is very limited. but we have known that tomato case, pollination is affected, and somewhere between 30 and 35 degrees C is the critical temperature for the pollination. So growers want to avoid that. How long they can tolerate under that temperature, I don't know. Probably plants can take, instantaneous increase of that temperature, okay. However, if it is prolonged, the high temperature continuing, I would be really concerned. So it's really not so much information, high temperature, upper limitation. If you go to ASMET, there are two combinations of high and low. One is for warmer crop, the other one is a winter crop. So the base temperature is different and the upper temperature limit, I think, is different too. So it's very much rough right now. But again, as long as in the linear range, you can pretty much explain by average temperature. And then just a minor incidence of exceeding temperature wouldn't affect. You can actually tell by number, elimination of that little high temperature peak wouldn't affect the cumulative temperature of 10 weeks or whatever, maybe more, 10 months in tomato case. So the minor influence. But that's all about, how much time the plants are subject to that temperature. So it's a good question, though. It's a very good question.
Would we correlate it with like yield? Would that be
Oh, yeah.
Your yield drops and
Yeah.
temperatures are too
Yeah.
low,
Yes.
so that-
Yes. You can explain many things by looking at temperature data. Yeah. That's why we record. And we are supposed to look at temperature record every day. Yeah. Okay. Any other questions? All right. So this is a super simple version of how to use the heat unit idea in a production system. And then I just wanted to use this so that you can see that small difference in terms of average temperature could create large difference in a production rate. So this is very simple, okay? So you actually do the average temperature in maybe 5-minute, log data, more accurate way. But this one is assuming we have a very nice temperature control, okay? Maybe in a veggie box. By the way, you will get to see veggie box in sometime soon. Assuming you have a nice temperature control, and 24 average is 20 degrees C, okay? Maybe lettuce growing. And the base temperature of this crop is 5 degrees C, okay? 5 degrees C. So, and then you know that by experiment, from seed to harvest under this constant temperature or the average temperature 20 of this particular crop, 42 days, that's the required. And then, whatever the constant light intensity, right? So everything is controlled. And then in that case, you compute cumulative temperature. So basically the cumulative heat unit. And then that is for 42 days. So that's 630 degree days. How did you do that? 20, which is the average, daily average, minus 5 base temperature times 42. Okay, because it's the perfect control, so it's easy to, just the average temperature minus base times days. In the field and greenhouse, you got to, get the every day, degree days, and then sum up. But in this case, just simplified example. So my degree days to get the harvest of the crop is 630 degree days. Do you want to ask a question now?
Go ahead.
Okay, all right. So how do you use this information is the next part of this slide. What if I want to slow down, or maybe the different example. What if I can't, spend so much time or there's so much energy to increase the temperature up to 20, so I want to reduce the temperature to 18 degrees C. Maybe this is cold outside or something, okay? So I want to do 18 degrees C. That's 2 degrees, and I would expect it's only 2 degrees, not too much. But actually, if you do this computation, so it's a linear range, all right? So that's why you can do this computation. 630-degree days from seed to harvest divided by 18 minus 5. So that's 18-degree average minus base temperature. So that can tell you how many days actually takes in this temperature condition. And then that is telling 48.46 days. So the original one is 42 days, and now 48.46 days. Actually, lowering temperature by 2 degrees slow down by 6 days, which is huge, don't you think? You are targeting certain day to ship your plants or ship your produce. 6-day difference is you might lose your job, right, TJ? Yeah. Or business. Yeah. So that's very important. That's why you need to pay attention. Yeah. All right. Okay, any question? Okay.
Seed, the harvest, just taken off the seed packet? The days?
Oh. This is just an example, so you can think anything. Maybe seeding. Maybe seeding day to harvest, 42 days. Lettuce is like that, 6 weeks.
But your peppers are...
Oh, no, wait, yeah.
3 months?
Yeah. Okay. But you can apply the same way to different crops. Okay. Are you all right? Okay, good. The next section of today is DIF. The DIF is the technology for controlling stem elongation for floriculture crop. It's really fascinating. I think it's a revolutionary technology developed by the floriculture group because it's a non-chemical control. Floriculture, you use a lot of chemicals. Not just pesticides, but also growth regulators to make the plant smaller, make the plant stretched. Lot of those used. But this is one of the technologies, non-chemical control. The technology is based on the traditional understanding of thermal periodicity. So temperature is affecting plant growth, and then when temperature difference is large, the growth rate is affected. And then in this case, more like a morphology and shape of the plant. So before going into deeper detail, so the guy who needs to get credit is Royal Hines, who is already retired professor. But I was inspired by his approach, and maybe one of the reasons I'm standing in front of you is probably his work inspired when I was an undergraduate and graduate student. Anyway, so the diff is the difference between day and temperature. DIF is coming from the first 3 letters of difference. Difference between day temperature and night temperature. And then diff is actually the temperature difference between daytime and nighttime. And always day temperature minus night temperature. Day temperature, average day temperature minus average night temperature. So you need to record the temperature all the time to compute the average temperature from the day, average temperature from the night to compute the diff. And then when temperature is high in the day, low in the night, which is typical condition in most of the growing systems, that we call positive diff. But for this particular application of this technology, growers might want to have negative diff, which is higher night temperature than day temperature. So warmer at night than day, which is kind of counterintuitive because it's not normal, but it works really well for a certain case. For controlling stem. 0 diff is day temperature equal to night temperature, average. Average temperature of the day equals to night temperature. Okay, see that graph, picture. So this is the Easter lily pot production. I don't know who now buy Easter lilies at Easter day. No, not anymore. But it used to be, right? The major, if I understand correct, major floriculture species targeted to Easter day. But anyway, so the quality of the Easter lily is very important, and one of the quality attributes is the height of the plant. If the height is very short, it's compact but big flower, that's the best Easter lily pot plant, if you are familiar with. So this one is showing how temperature affects the Easter lily stem elongation. So the Easter lily has already flower buds and forced to develop that. And then they stop the elongation at certain stage, and then you can sell at that stage, right? So this is basically forcing temperature, meaning the Easter lilies are ready to go, and then in the greenhouse, different temperatures and developing the flowers. Yes.
Doesn't that also have to do with dating? Depending on
Yeah, it's much. Yeah, so day length. Let's assume day length is the same in our talk, because we are talking about the temperature effect. So the forcing is the after initiation of flowers. Okay, forcing time is the after initiation of flowers. So initiation of flower may be affected by day length, but I'm not 100% sure what is maybe only temperature is affecting. The chilling temperature to induce the flower buds, and then after that, that's probably most likely. Yes.
How do you know that, or like if you're designing an experiment, how do you separate the fact that just the average temperature is higher, if the daytime temperature is higher? How do you separate the effects of average day temperature or average temperature and the dip?
Yeah, so how do we separate the average temperature effect and, for example, day temperature effect? You can't clearly separate. So that's why in this particular side, low temperature side, it's slightly reduced in terms of development rate. So the flowers are underdeveloped compared to the high temperature. But there's a way to design that. Maintain the average temperature equal, but changing day temperature and night temperature to create different diff. I'll show you one example later. Good question, though. So anyway, so for understanding, diff, is this the first time or you have had diff already? First time. Okay, good. So this experiment, again, is studied. So the leaves, number of leaves are already determined, and then flower bud is already developed, and then forcing that flower bud and stem develop at different temperature conditions. And then this one is the night temperature is fixed, 18 degrees C across the 5 treatments. And they only change the day temperature, in this case, 14 degrees C, 18 degrees C, 22, 26, and 30. So the interval of the temperature or increment is 4 degrees C. So if you look at the plant height, it's clearly linearly responding to that temperature treatments, right? And then if you compute the diff, day temperature minus night temperature 18. So this is minus 4 diff. This is 0 diff. This is plus 4 diff. This is 8, right, diff. And then this is 12 diff, 12 degrees. Increasing diff increase the internode length, so that the height is higher, right? Right. This is opposite. So this time they fixed the daytime temperature 26 degrees C. So all conditions at 26 degrees C daytime temperature. They have, by the way, sophisticated greenhouse, so they can set any temperature in so many compartments. But anyway, 26 degrees C during the day, nighttime temperature 14, 18, 22, 26, 30. If you look at the diff, nighttime 14, daytime 26, so 26 minus 14. Diff is always day minus nighttime, so 12. And the next one is 8, right? And next one is 4. And next one is 0. Next one is minus 4. So the nighttime is warmer than daytime. And you can see that higher the diff or greater the diff, then your plants are taller, right? So again, grower want to make the plants shorter, and then usually they use chemical growth regulators to inhibit gibberellic acid, all right? So that application is not necessary anymore with this technology. So it's quite interesting. And this is another fascinating result. So the temperature 14, so it's a 0 diff. This is different temperature combination, 18, 22, 26, 13, all 0 diff. And then look at the perfect, the temperature, the stem length, the plant height, pretty much determined by, it's fascinating, don't you think? Yeah, all right. So this one is the plant height plotted over the diff. So the diff is the negative value all the way to positive value, right? And then they also looked at the interaction between temperature and light, and they didn't see interaction between temperature and light. So that means regardless of the season, this technology can work to stretch or reduce the stem length, which is quite nice. Okay, there's up and down, okay, so because it's a biological data, but pretty much in that linear response. Okay, so that's what I was talking about. So this one is tomato plants experiment in Chiba, where I came from. One of the graduate students did this experiment, never published. I don't think that he published eventually, but just to demonstrate the diff works on tomato plants also, because so much data was, basically so much research was toward floriculture species and not so much for vegetable crop species, so we wanted to test in a vegetable species. And then we tested in a young seedlings, not the mature plants. But I think it's interesting to see how mature tomato plants can respond to. But this one is minus 12 diff and 0 diff and 12, positive 12 diff. And this one was designed so that average temperature is equal, so that separating effect of average temperature from the diff influence. So that's one way to test or design the experiment. And then I usually pay attention to those things when we design the experiment. Particularly like, tomatoes, it's continuously growing, so you can't really tell if it is because of the growth enhanced or because of the stem elongation enhanced if you just look at the stem height. So that's why we design this way. So the average temperature is always, regardless, 22 degrees C in this case. All right. Okay, so the diff, yes, TJ.
Is that 4 degrees kind of a minimum? Or is there a minimum temperature difference in order to
Oh.
response?
Which way? Reduce the stem elongation or increase the...
Either way, if you're -1 or you're +1, it's going to either shorten a certain amount or...
So this is a Fahrenheit, right? So yeah, so this is the difference between day and night. So you got to multiply by 0.56 to get Celsius degree difference. So by looking at this data, yeah, I think 2 degrees or 3 degrees could, C, Celsius, 2 to 3 degrees C degree difference could generate some difference. Okay, so that understanding developed very sophisticated temperature-based stem elongation control, which is called graphical tracking. And that side reading talks about that graphical tracking. So you want the target height, right? Your product, in this case, Easter Lily, is the best, premium price at that height, big flower and this height. Never go beyond that or below that. So you have a target height right here, and then acceptable range, right? And then based on your experience of, previous 10 years of experience or so, you kind of know that the plant height should be tracked within this range, January, February, March, toward the shipping time. And then you can actually tweak the temperature by looking at the actual stem length relative to the target range. For example, so this solid line is a target range. You want to make the plants falling in that, in whatever corresponding timing of the production. And then the dot lines or broken line is the actual plant height. So grower every day, measure the height. And then based on that difference, which is exceeding the target range this particular day, so, the plants are a little too high, too stretched. You want to slow down the stem elongation rate. So what they did was creating negative diff, -4, -5 degrees C, and then slow down the stem elongation. So to do that, they set night temperature 17, day temperature 12, and then 5 degree negative diff. And then it actually come into the target range. So it's okay. So instead of keeping that range, because it might go below the lower target line, so they increase the diff to start, stretching again, and do the same, changing diff like that, and tracking. And then final size of the plant is perfect. It's really high technique, and only the greenhouse growers who have sophisticated, temperature control system can do this. But actually, some of them are doing that. All right. Okay. So summary of the slide. Day temperature affects photosynthesis, transpiration. Night temperature affects dark respiration, and day-night temperature difference affects stem elongation. And then one more thing we didn't mention today is the balance of the growth, reproductive and vegetative. We probably talk about that when we talk about carbohydrate allocation. And 24 average temperature is cumulative temperature, either or affect the development rate of the plants. Development rate meaning, the number of leaves, increase of number of leaves or number of flowers increase. So that's, the addition of new organs is the development rate specifically, okay? Versus growth is more generic term. It could be biomass increase, it could be height or the size of the plant, but when you talk development rate, it's an increasing number of new organs. All right? Okay, so that's it.